Electropages is here at PCIM Nuremberg 2024, and we are at the Avnet Silica stand where they've got some pretty exciting stuff. Now, Avnet Silica we all know and love as a distributor of key semiconductor products. So today we interviewed a really great guy who showed us some of the stuff that they're working on.
And last time we came here at Embedded World, about a few months ago, we saw some really cool stuff that you guys are showing off. And now at PCIM, we're looking at some power stuff. So, take me through what's going on with some of these demonstrations.
What we have here is an onsemi charging demo. So what this demo does is you have here the input, then it does a PFC stage that is bidirectional, so energy can go in and out. And what we do have here is then a DC to DC. That is needed to transform the internal bus voltage of 800 volts to the bus voltage of the car. And what we can do here as well is having it bidirectional. So when you have the car here, it can charge from either the grid or the photovoltaics you have. And if you don't have any energy from the photovoltaics and you don't want to take any energy from the grid either,
just been done with back in.
Yeah, exactly. And this one is a 25 kilowatt demo. So when we put it in perspective, it can basically power
a whole house.
Two houses.
Two houses? Well, that depends on how much stuff you've got in your house.
Yeah, normally the household power is
10
around
to 8. 10. And this is my house, so I've got a service that could be up to like 15 at times. But that is really impressive. So you can do two houses from one unit. So do you think that would mean that maybe two homes attached to each other would share one charging unit? Do you think it would be a case of two separate charging units anyway?
I mean, it depends. You can use like one of these that's 25 kilowatts, and you scale that one down to two 11 kilowatts, for example. And then you have two charging slots, two cars, and you can just via software kind of check where the energy is flowing, where it's ready to go.
Now, looking at this design, I personally find it quite unusual that the PCB itself, it looks like a 1.6 millimeter, in terms of thickness. I'm surprised how thin it is, being able to deliver 25 kilowatts of power.
It's not the kind of thickness of the PCB, it's the thickness of the tracks that are here in here. And
so we're talking really, really wide tracks here. Yes. But even then, that track can deliver 25 kilowatts.
Yes.
What current are we talking about?
Oh, Jesus, I need to do some measurements there, but I think the peak current is 80 amps about.
80 amps.
But it's an LLC, so it's always a sine wave, a half sine wave.
Of course.
So
the average current. Yeah.
Average current is lower than this. So it's always we're always looking at the peak current, and at the end we're looking at the copper track. So it can get warm. So it's not really.
But still though, for 80 amps at 25 kilowatts, it's smaller than I thought it would be. Because you see these chunky power cables coming in, you think that would make sense for me. But then you've got these thin traces, and it's not a problem.
Yeah. What you have is here you have the metal layer is actually thicker than usual. Because you can,
right, so you're not your typical 35 micron, it might be something like 80 or something.
Yes.
Yeah. And so you're doubling that current capacity. Oh, okay, that actually makes sense. I take it, do you use like double layer as well? So you've got tracks on top and bottom to try and double up the...
Normally you use 8 to 16 layers in here to just accompany...
So you have a copper layer,
Yeah. 8 to 16, because what you need to do is you have power tracks, and what you see here is the control board. There's actually a Xilinx SoC one. You need to have all the measurements done as well.
Yeah.
All the sensors, all the controlling, all the steering. And so you need lots of layers.
And I love how all of this, the entire 25 kilowatt power system is being controlled with this tiny little module right on the side here. But I think what we really need to look at, because this is obviously impressive, but what is more impressive is the technology that's powering. So what is it in here that's essentially able to conduct at 25 kilowatts? Because I imagine there's going to be some switching devices.
Yes, there is. It's below here, really. There's a F2 module from onsemi with 10 milliohms, roughly, of RDS on. So
what kind of technology is that?
Silicon carbide.
Right.
It's all silicon carbide.
Oh, it's all silicon. Yeah. Okay, fantastic. And so that is basically, so you basically managed to use SiC to not only provide that higher power capability in smaller units, but you've also been able to do, I suspect, that at higher efficiency as well?
Yes. Especially in the lower ends of the power usage.
Right.
Because when you compare an IGBT and the silicon carbide at nominal load, there's not so much difference. Yeah. But when you have the whole thing compared at partial loads, the silicon carbide is way more efficient because you don't have the saturation.
Because I was about to say, I'm quite aware that DC power supplies tend to have that issue where if you're not drawing much, the inefficiencies actually go up, and you actually have to use them almost at their maximum to even be able to get close to like 90, 93, 98. So what kind of efficiency are we looking at on this board here?
Between 96 and 98. And if you look at the high-power DC chargers that are out there, the 400 kilowatts, big ones, in the worst-case situation, they have 94% of efficiency.
25 kilowatts.
Yes.
And you've got 98 to 96, or 94 to 96 or so.
Yeah, somewhere there in the 90, 94.
So that you were talking, what, 100 watts at most of leakage, maybe? I mean,
it's not much, right?
Not much at all. And actually, you could easily dissipate that. Like I say, one little fan, big heat sink, chucking heat out. So if you had to build this, not using silicon carbide, but using standard silicon technologies, how much bigger would it be, do you think? What challenges would that design have?
I would, if you spend a lot of time in kind of figuring out how to get the package density right and stuff, I think if you would do the same design in silicon carbide in best effort packaging, you will get 50% smaller than this one, and you could have this one in the same size, about 90. Right. So this one is clearly this one is a real life demonstrator and lab equipment. So onsemi is using these things in the lab to measure their new devices. So actually, these ones are really tortured devices. So
now, when I'm looking at this one to me looks like a three-phase system compared to that one. Is that correct?
Yeah, this is a three-phase input system.
Yep.
And it translates it to an 800-volt bus.
Yep.
And then you have 800-volt in, and you have...
Oh, so you use these two together?
Yes, you use them
together.
together.
Right, so that's taking the three-phase, pushes it into a single phase, and the single phase then knocks that down DCs.
Yes. Because you need for everything that is touched by an end user needs to be insulated.
And so that would mean that this comes in from the mains. We're talking like overhead mains where you've got your three phases. Because obviously every third house will be connected to different phases. Depending on how it's structured.
In the UK, yes. In the Central European area, you have always three phases.
Oh, really?
You have
what voltage are?
380. You have 230.
So every home has a three-phase system?
Yes.
Oh, lucky.
Yes.
We're going to get one phase. Okay.
Yeah, so for a one-phase system, I wouldn't use this whole construction. You can use just one of this.
Just one unit of that, and it'll do the job.
Exactly.
Oh, okay. So here you need to balance that phase, and so you have that secondary system. Yes. So when you push power back, so let's say you've got your car connected to the system, it's charged up, and you want to dump the power back into the home. Would it not use this, and it only comes from here, or would it go back into this before?
Back into this.
Back into this,
yes.
And then it goes back into your home.
Yes.
Because the home's three-phase.
Yes.
Whereas we wouldn't do that because we would just need one block in the UK because
yes,
comes out goes back in. Okay, that makes a lot of sense then. Okay.
And the trickery here really is when you feed back to the grid, you always need to maintain a certain control area.
Yeah.
And it really depends, and that's difficult. If you're kind of just feeding and always kind of grid connected, it's always the arc clock transformation that you can use in normal motor control, really. There you can control the current and everything.
Yeah.
If you want to make this kind of blackout proof, for example, when there are severe storms that cutting the overhead lines and you need to be self-sufficient for a few days till they fix it, then you need to apply a different algorithm. So that's more tricky to do, really. For single phase, not at all. For three phase, it's then more tricky to do.
I can imagine. Yeah. Okay, so there's something around the corner I also want to get on the camera as well, and it looks quite exciting. And I do believe you're an enthusiast in this area. So let's go take a look. Let's go. So to those walking by, this would just look like your regular motorbike, but it's not.
It's not. It's an electric one. So this is actually a prototype of the Flex Performance Primo. It's a fully electric motorbike. It has 50 kilowatts peak power, perfect for every riding, you can imagine. For most of the stuff is actually a little bit overpowered, especially for people in my riding level, so I would trim it down. The actually unique thing what this bike has is here. It has a virtual clutch, so it can work like a clutch really, or you can set it to recuperation where the back wheel is used to kind of feed energy back
into the system.
So it's handy when you have long descents, how to do riding, something like this. And yeah,
So I've got a question for you about this, and I think you answered it earlier on, but I'd like to explain, well, I'd like you to explain the views about it. So when I saw this bike, I was a bit shocked to see that it had a chain. And I was asking, why have you not just got a motor on the back wheel, you know, like you would, let's say, an electric bike? So what's going on there, and why is it that why is essentially the chain important?
When you put the motor in the back, in the wheel, you have a big undamped mass here, which gets really unhandy when it comes to higher speeds and higher rotation speeds of the wheel. So with all the motorbikes, what you want to have is maneuverability in all cases. And to ensure maneuverability, the wheel and everything that is connected to the wheel must be as light as possible. So that's why the motor is down there.
Now, just to very quickly explain, when Thomas says about high speed, what he really means is the legal speed that he's allowed to drive. No more than the legal speed was what we talked about. So when
Except
traveling
in races. This one is also a race bike.
Oh,
so
right, it's a race bike. Okay,
it's a
so
race bike,
what kind of top speed are we looking at, do you think?
The normal, when you compare it to combustion engines, normally 110 to 120 kilometers per hour, something like that.
Right.
So motocross is not really fast, you just fall fast.
You just fall fast. So if this was driven in the UK, this would be 70 miles an hour max. Can't go any more than that. And that should be all right.
Yeah.
So in terms of the technology that's powering this bike, again, is it using silicon carbide?
Yes.
Or, and how is that helping in this design compared to using a silicon device?
The thing is, when you look at bikes like this, you always need peak power in a very short manner.
For high acceleration.
For high acceleration, for just getting the momentum where you need to kind of get over a log, get past a tree or over stone, whatever. But for kind of the long endurance, you have very little actually of the maximum power used for the bike. So what you need to have is high efficiency on the high power end, high efficiency in the lower power ranges. And silicon carbide is the only thing to really do this.
As we said earlier, when you have silicon devices on the lower end, the efficiency is very, very low.
Yeah.
So what you want is something that's just balanced out for the entire thing. So when you're slowing fast or you're kind of like just cruising along, the efficiency always needs to be high to maximize the range. So what kind of range would this go for? And what kind of power, how big's the battery in this thing?
I mean, range with these kind of bikes is always a bit relative. So
depends how you ride it.
How you ride it, how the rider is and everything. So this comes in later somewhere in the 8 kilowatt-ish range. So it will be sufficient. So you can do a whole motocross race. You can do like 3-4 hours of hard enduro riding. So when you go for 3 to 4 hours of hard enduro riding and you have a decent kind of condition, you're done. So
and whereabout is the battery in this design?
Battery is here.
Oh, blimey. So is that a heat sink for the battery?
Yes.
Oh, wow. So that's quite serious, that is.
That's a serious block of batteries.
Yeah, no. Because I was thinking you might put it inside the frame or something to try and distribute the weight of it, but you wouldn't do that.
With here, you're also in the undamped mass area, so you always want to have all the mass
right here.
So that's why I like the combustion engine equivalents. When you look at the Dakar Rally, for example, they all have the fuel tanks down here because it's better maneuverability. And so what we're trying is to kind of have everything that is heavy.
Now, I think it's fair to say that everything we've been shown today clearly just demonstrates the importance of silicon carbide in modern designs. And so my final question to you, for the viewers out there, if they want to get involved with Avnet's silicon carbide solutions, what would you recommend that they do?
Write me a message on LinkedIn.
LinkedIn, you heard it here first. Fantastic. Well, thank you for everything you've shown us today.
Yep.